Okay, so today I want to discuss some of the most fundamental aspects of projective geometry. In particular, the idea of projections and the idea of duality. And these are really very close to the heart of the subject. But before that, I really want to actually define projective geometry, at least on the projective plane. So far, we've been thinking of it a lot in terms of geometry on the Euclidean plane, and then adding the idea that parallel lines meet at infinity, which is not something which happens in normal Euclidean geometry. So this can be done by supposing there are some extra points at infinity, and this is how Desargues described projective geometry. So what is actually posited is that in addition to all the finite points like the Euclidean 2D plane, there is a line at infinity. One could even think of it as a circle of infinite radius at infinity. A circle of infinite radius is basically a line, okay? So for every direction you have a particular point at infinity where lines pointing in that direction would meet. That's the old style view. The more traditional modern view is that projective geometry on the plane ought to be thought of from a three-dimensional perspective. And what the projective plane actually is the set of all lines which pass through the origin 0, 0, 0 in 3D space. Okay, so this isn't something which I'd like you to get too hung up on at the moment, because I just wanted to tell you a proper definition. I think it takes some getting one's head around this idea, but this is really what the projective plane is. And this makes a lot of sense. So, in fact, it's not really a plane at all as far as really geometrically. It's a set of lines that go through the origin in 3D space, and each of those lines can be visualized as a point on a plane which has a height of 1 above the 0, 0, 0 point. So, for example, this point here is actually just a representation of this line. It's just a place where this line skewers through this plane. But if you imagine this line tilting, so it's almost horizontal, then this point will fly off to infinity. And as this line tilts even further, so it's beyond the horizontal XY plane position, the other side of the line will poke through the plane at the opposite end. So a point appears to rush off to infinity and then reappear on the plane at the other side. And one can see in this way that there is a kind of circle or line of points at infinity. But anyway, this is still all kind of vague. I mean, it's picture based. But this three-dimensional perspective can be formalized using things called homogeneous coordinates, which are not something I'm going to go into today. So personally, I think one of the most honest ways to really describe projective geometry is in terms of axioms. In that way, we don't even have to think about what a point or a line actually are. We can just think of them as entities which obey certain rules. And that's good in a way, because it allows us to abstract beyond the visual spaces which we're used to thinking about and look at other mathematical systems which act just like the projective plane, for example. So Euclid did this kind of idea with standard geometry. He set up various axioms. So many people have found different ways to set up projective geometry axiomatically. There's lots of different approaches. I'm going to tell you one that I saw in a paper by Brendan Hassett, which may be based on the work of Coexeter. I'm not 100% sure, but basically the axioms are like this. 2 points, distinct points, lie on precisely one line. Given any 2 points, there's just one line that goes through those. Given any 2 lines, those lines meet at exactly 1 point. And there exist non-collinear points, okay? So this is maybe a funny sounding one. The reason why we have this one in is because people look at discrete versions of projective geometry. So far we've just been talking about kind of versions in the continuum, where we have a whole plane, infinite number of points, infinite number of lines, lots of freedom. But you can also think about finite schemes, where you only have, say, 20 points or something. And so these extra axioms allow you to do something like projective geometry in these more exotic situations. And they are that there exists at least 3 non-collinear points. Collinear points are points which lie in a straight line. And also every line has at least 3 points. So these are known as the incidence axioms. And to get proper projective geometry, you have to assume one more thing. And the extra assumption is, well, you can assume several different things. That's why, as I say, the axiomatizations vary. But in this particular thing that I read, Desargues' theorem holds true. Now that might seem strange because Desargues' theorem is supposed to be a result of projective geometry. But as I tried to explain in the last lecture, it's kind of intuitive in some ways. But anyway, if you want to axiomatize projective geometry, this is one way to do it, and it's probably the easiest one to explain. I don't want to get bogged down with going through the axiomatics. Just to recall what Desargues' theorem says, what it basically says is that if you draw a red triangle and you draw a blue triangle, and those 2 triangles have their feature that there is a point V which they are perspective from, in the sense that you can draw lines out from V which pass through the vertices of the red and the blue triangles, then the corresponding edges meet at 3 points which are collinear, lie upon a straight line. If you take that for granted as well, then you have projective geometry on the plane. The important thing is that here lines and points play precisely equivalent roles, in the sense that every pair of points defines a unique line. We're used to that idea, but also here every pair of lines defines a unique point. So in fact, theoretically, thinking purely abstractly, these objects are kind of dual to one another. And this is a very real and important aspect of projective geometry, because in fact, it basically says that you can take any theorem about the projective plane, about lines and points, and wherever it talks about lines, you can replace it with the word point, and wherever it talks about point, you put the word line, and you get a consistent extra result. So every result has a kind of dual. A perspective in projective geometry is a manner by which objects in one shape can be related to objects in another shape. And we shall see, as there is a duality between lines and points, there are 2 kinds of perspectives. This is a kind of perspective which has a point, which is sort of done through a point, a so-called centre of perspectivity, this yellow point V. And what's happening here is that we're drawing lines through V, and we have these two objects, this red line with red points A1, A2, A3, and this blue line, B1, B2, B3. And what you're seeing here is a perspective between these two lines with respect to this centre of perspectivity V. Why is that so? Why is it said to be that? Because there are these two sequences of points. On the red line they have a sequence A1, A2, A3, and on the blue line the sequence B1, B2, B3. And you see that the corresponding members of the sequences are each on a line which passes through this centre point V. So, more visually, if we draw these lines through V, we can draw a line that goes through A1 and B1, so that puts them in correspondence. The next line puts A2 and B2 in correspondence. And this next line puts A3 and B3 in correspondence. And actually, if you think about it, the location of this line and of this point and these lines really sets its correspondence up from every point on the red line to every point on the blue line. So really, you could think of this as a perspectivity from one line to another. But just to speak of it a little more rigorously for a second, in general, you might not have points on a line. They might be on a triangle or something more general. So in general, if you have a sequence of points, say A1, A2, A3, and they're in perspective with another sequence of points, B1, B2, B3, with respect to some centre of perspective, what that means is that there is a line through A1 and B1 which passes through this centre of perspectivity, and there is a line through A2 and B2 which passes through the centre of perspectivity, and there is a line through B3 and C3 which passes through the centre of perspectivity, and so on and so forth. Okay, so in the previous case we were doing a perspectivity from one set of collinear points, A1, A2, A3, to another set of collinear points, A1 and B1, B2, B3, and we were using this centre of perspectivity V. Now in this case, basically it's the dual. It's the kind of dual of that idea. Rather than having two sets of three collinear points, we have two sets of three collinear lines. Line little a1, little a2, little a3. All those three lines meet at point big A. And lines little b1, little b2, and little b3, they all meet at this point B. And rather than having a centre of perspective, we have a line of perspective. If we have a sequence of lines, A1, A2, A3, and they don't necessarily have to be concurrent, and we have another sequence of lines, B1, B2, B3, well, we'll say that they're going to be in perspective with one another with respect to some with respect to some horizon of perspective, little v, when the lines A1 and A2 meet at a point on this line V, and when the corresponding lines B1 and B2 meet at some point of this horizon V, and when the corresponding lines A3 and B3 meet at a point on this horizon V, etc. the clearest way to say it, in my opinion, is that a couple of lines are going to be perspective when they meet at a common point on this horizon line. Just as in the case where we had a centre of perspective, a point in the previous case, it was kind of like the dual situation, where we said that a pair of points were perspective to one another when the line that passed through the two of them met the centre of perspective. Okay, so far we've introduced the idea of perspective and seen how it can be applied to both points and lines. Now I want to introduce the idea of a projection. So a projection is basically nothing more than a sequence of perspectives. So you can think of it as a transformation from a set of points to a set of points or lines or whatever. But basically, we say that two sets of objects are projective, or one can be reached by doing a projection from the other, if it's possible to do a sequence of perspectives to get from one to another. So for example, in this picture we have these three red points, and it's clear that by doing a perspective with centered at a yellow point on that, there's a perspective between these three red points and the three green points. And now we can do a second perspective from those green points using this orange center of perspective, and that then maps those green points to those blue points. So there's a sequence of perspectives that sends the red points to the blue points. So there's a projection from the red points to the blue points. And one may have projections from sets of lines to sets of points. One can have projections which correspond to a sequence of many perspectives. The idea of being able to combine perspectives and study what kind of geometric properties are unchanged is really one of the things that underlies the whole of projective geometry. So what I'd like to do now is to show a method by which one can find a projection from one generic line to another. It's not always possible to do that in one perspective, but it is always possible to do it in two. When I talk about lines, I'm really talking about, essentially, I'm talking about how to project three collinear points onto three collinear points. But once you define such a projection, it turns out that it will actually also send any of the other points on the line to the other line. So it basically does the job. So the first thing we're going to do is just to sort of try and find a origin of perspective by linking corresponding nodes. Okay, so you see that forms this triangle. If that had formed a single point, then we could have just done a single projection and we would be done. But as you can see, that's not the case. And so we're going to have to do a two-stage process. Our projection from this red line A to the blue line B is going to be a two-stage process. Okay, so we can use any two of these 3 points to create our origins of perspective. We need two origins of perspective, but for this case, we'll choose the place where this B1, so for this case, let's choose the place where this A2, B2 line crosses over with this A3, B3 line. That's going to be one of our points between A1, B1 and A2, B2. Oh, excuse me, that'd be there. Okay, and we'll call this one W. Okay, so now we have our centres of perspective. All we need is a kind of middle stone to hop from the line A1 to the line B1. In other words, we need a kind of auxiliary line. And we're going to construct that as a line from A1 to B3. Okay then, so let's do our projection from this red line to this green line M. So we'll get some lines. And we can do like so. So now, just to complete the process, what we want to do is to do another perspective from W, so using W as our origin of perspective to send this green line onto this blue line. When we do the perspective of M2, it's going to get sent to B2 because it lies upon that line. And automatically, since M3 equals B3, M3 is automatically going to get sent to itself under this perspectivity of the line M. So, indeed, we get what we wanted, which is basically that V gives us our perspectivity from the red line A to auxiliary line M, and then W gives us our perspectivity from the auxiliary line M to the sort of final destination line B. So that's it. And notice we've preserved the collinearity of points. Now, you should note that in general, a perspective, I think one can perhaps prove for oneself that a perspective always preserves the collinearity of points. But this idea that a sequence of perspectives does so is something quite remarkable. We're going to do a projection from this point A with the three lines that are concurrent on it to this point B with the three lines that are concurrent on it. It's really an analogous procedure to the one we did before, just with the notions of points and lines kind of swapped round. So rather than before where we were using centres of perspective, we're going to start now by finding two horizons of perspective, because we're going to do two perspectivities to get from A to B. So this is our first one. It goes through A2, B2 and A3, B3. We shall call that one V. And our second line that we're going to use, we shall call W. That goes through A2, B2 as well, or also goes through A1, B1. Now then, the final thing we need is our auxiliary point. Now to make our auxiliary point M, we're going to use A1 and B3. So it's just a point this time. So let's use it there. And it doesn't seem like we've been using purple enough recently. So there's big M. Okay. So now what we're going to do is we're going to find out how these three lines concurrent upon A end up getting sort of mapped onto B by this perspective via this yellow line V. How they get mapped onto M, via this yellow line V. So let's have a look. What about A1? Well, A1, it just goes straight down to the yellow line and it just bounces straight off it. So that just basically means that, as last time, M1 is equal to A1. What about A2? Well, that one is going to get sent down to the yellow line here, and at that point it's going to get bounced off this yellow line towards M, and so it's going to get sent up here. Déjà vu? And I guess maybe we should call that line M2, since it is genuinely original. M2 in all its glory. And finally, if we look at what A3 becomes, it bounces off this yellow line, and then it basically becomes B3 again. So we have a very similar situation to last time. Okay, so now we've basically done our perspective from A to M. All that remains is to use this green line, which I thought was called W. Yes, so we use this green line to do a perspectivity from M onto the blue line. So let's see what happens there. Well, we'll use M1, which is A1. Well, that just goes straight down here to this place, and then it bounces onto B1. So that's good. M1 gets mapped to B1. What about M2? Well, that maps straight down here, straight onto the horizon, straight to B2. Great. What about M3? M3 is B3, always will be. So that's the end of the story. We have our general perspective, we have our general projection from one set of concurrent lines to another.